Section 4.
Okay, starting the recording. Now it's official.
Okay.
Section 4.
4, question 36.
Okay.
After we've built that model, so without controlling for person coping, that means then we're taking out one of the centered variables in our model.
So the question was about, just make sure the Zoomers can hear, was about this one and presumably 37. Yes, 37 I'm guessing is the issue more than 36.
Well, I'm setting up the model
I had to guess.
for it.
So the short answer is that all questions should be answered with the same model. So it does not require a separate model. What I'm looking for is you to identify what kind of effect this is, given the description, and then add to the model requests, I will say. This is a LINCOM estimate or contest 1D statement to create it. Alternatively, if you fit a different model in which this parameter was given directly by a fixed effect, but you didn't have any other fixed effects in the model, you will get the right slope most likely, but you may not get the right standard error, because that is based on the model for the variance, and that model will have too much variance in it relative to the one that the rest of the questions are based on.
Okay, so in the contest 1D, then there should be 3 numbers.
3 numbers.
And then instead of 0, 1, 1, one of the ones needs to go to a 0 then, because if I'm not controlling for that, then that means I'm turning it off, right?
Good guess, but no.
Okay.
You would think that, but it doesn't work that way in this case.
Okay. All right. I will keep poking at it.
Okay.
And I don't know what question to ask next. So.
Okay. I would, without controlling for level 1, I would do some searches through your notes and the materials to look for that as an idea.
Okay.
Now, that should lead you in the right direction. Other homework questions while we have it up here. So do you remember my rule about 15 minutes?
Yeah.
I'd like to amend the rule slightly. If after 15 minutes you're stuck on something with no end in sight, stop, reread the directions, and then send me an email if the answer is not in the directions. Because I've answered several questions where the issue was either not reporting to enough decimal places for the -2 log likelihood, and there's instructions on how to get that out of each package here, as well as what happens if your intercept is not correct. That means it's a centering problem. How to compute pseudo R-square is also described up in here as well. So I've answered several questions about those things that the instructions were designed to cover, and the section-specific instructions for each of the models should tell you what goes in the model. So for section 2, it's an empty model, for example. Section 3 is asking you to center person coping at 50. And section 4 is asking you to center site mean coping at 50 after controlling for person coping, still centered at 50. So that should hopefully get you in the right spot, and then you can use the examples to figure out what your code should look like. So if after 15 minutes you're stuck, rereading the instructions didn't help, then it's time to ask for help. So we have office hours today?
Yep.
Still in the other place?
Yep, the EPL Grad Lab.
Okay, office hours at 2 o'clock today, tomorrow at 3:30 to Thursday, or yeah, that's it. And then homework is due, but then we go back to our regular cycle. So.
Got it.
Got it.
Fixed it.
Excellent. Glad to hear it.
it.
Okay, then if you don't already have it, I did post over the weekend a new lecture 4. It is a lot of brand new content, and example 4 is a very different version of the same stories than the last time I did it 4 years ago. So I've been working on these. I hope that it makes it better and less confusing, but also more correct than relative to what I had before. So we're ready to dive into that. That works for folks? Lecture 4-ish? All right, let me get rid of this. And here we are. So, new concepts, random slopes and cross-level interactions. That's the main idea, but before we do new stuff, how about some old stuff? Yeah, we can't just jump right in, right? We need to take a breath and just sort of ease our way in. At least I do. So this was the review of the very first lecture on this topic. I think it was lecture 2. where we went through the process of empty models and understanding kinds of variance. So this is the beginning of any multi-level analysis. It's just figuring out how much variance you have of how many kinds. So in this context, we're dealing with observations nested in clusters. So there's only really 2 kinds of sampling and 2 kinds of variance at a minimum. After we finish random slopes and cross-level interactions, we'll move on to cross designs, where there's 3 dimensions of sampling, and then extensions into the world of generalized and multivariate. So, but for now, just 2. So empty model looks like this. There are only 3 parameters: fixed intercept, which is the mean of the cluster means for our outcome; random intercept variance at level 2, which tells us how different our clusters are on average; and level 1 residual, which tells us how different our people are within the clusters. So this is an orthogonal partitioning of variance. It's between site, or let's go cluster today, between cluster versus within cluster. So U's and E's are not correlated. It will break the system if they were to be correlated. We can compute an intra-class correlation. If you don't see a number after it, just assume it's this regular kind, which tells you the proportion of variance that is between clusters. It's also an effect size for how much dependency you have due to cluster mean differences. And it is also the average correlation of people from the same cluster. So you can think of that number any of those 3 ways, whichever works best for you. And if you want to be able to explain why some clusters have higher means than others, what kind of predictors do you need? If you're interested in explaining why some clusters are higher than others in the outcome, what kind of predictors? Level 1 or level 2?
Level 2.
2, yeah, cluster characteristics explain why some clusters are higher on average, things that are constant over the cluster, over the people within a cluster, I should say. Then we talked about level 1 predictors, and things got a little uglier, right? A little uglier, but not as ugly as they're going to get. I gotta be honest there. So the tricky part with level 1 predictors, they're always level 2 predictors too, almost always. So for the same reasons that we're worried about cluster dependency and doing a multi-level model with respect to our outcome, we need to worry about cluster differences within our level 1 predictors at the same time. So there's 3 options in general by which you can distinguish different slopes at different levels for a person predictor. There's my preferred cluster mean centering, which is available within the univariate models that we're currently looking at, where the software can predict 1 column at a time. And that is where you do the job ahead of time of carving up your level 1 predictor. So you have just its within cluster variation going into level 1. That means it's going to be a within slope, no matter what. And if you put in the cluster mean at level 2, that's going to be the between slope, no matter what, because these 2 predictors are uncorrelated. So predictors at different levels are not correlated. The only way they can be correlated is because of Trojan horse variance that's like sneaking in. I'm going to stick with that analogy. The level 2 part of a level 1 predictor can be related to level 2 things, but not the level 1 part. That was one of the things I was hoping to reiterate, demonstrate, elaborate in your homework. If you stare at a correlation matrix of your within and between and original variables, you'll see a pattern there with respect to that. Number 2, grand mean centering or constant centering, my less preferred version because it's easier to screw up. This is where we don't carve up the variable into its parts. We let the model do it statistically. So after controlling for the cluster mean, the level 1 slope becomes within, and the level 2 slope is this contextual thing. And the way that these relate to each other, do you remember? How do I get back and forth? How do within and contextual relate to between?
Because within plus contextual equals between.
Yeah, within plus contextual equals between. Between minus within equals contextual. It will help you if you just memorize that. Does that count as memorizing an equation? It's just subtraction, right? That's not so bad. But the logic of it is contextual is the difference. Contextual is the extra impact of the cluster above and beyond the original level 1 person predictor's information. So if you add what the level 1 predictor brings to the table plus the extra that the cluster mean gives you, that gives you the full between effect that would be responsible for level 2 reduction in variance. Cough, cough, homework question. And then there's latent centering, which I only waved my hand at for now, which is the idea of treating the predictor X the same as the outcome and letting the model figure out how much of its variance is between and how much is within, and using those latent variables as your predictors instead. That's later in the semester because that requires a different approach to specification and estimation. So then, where we're headed now is changing from fixed slopes to random slopes of our level 1 predictor. So the term fixed means every cluster gets the same slope. We're assuming that the effect of this person predictor on my person outcomes has nothing to do with what cluster you're from. Random slope means each cluster gets their own. More specifically, we're going to have a variance across the slopes, across clusters. Variance of the slope across clusters. And a new kind of interaction term will be needed to explain that additional source of cluster differences, which is known as a cross-level interaction. So that's the topic of this giant lecture 4, which will probably take at least 2 weeks, maybe 3. We'll see. We'll see, you know. I'm pretty bad at estimating how long things take, so I've just given up. We're just going to see how long it takes. All right, you ready for this? No. That's fair. I did ask. Can we pretend like we're ready for this?
Oh, yeah.
Yay!
Get it.
I love it.
Yeah, and when I hear that, and I start doing the pom-pom routine in my head to that song. Y'all ready for this? Yeah, I know, that's in my head right now. Thanks to myself. All right, how about some pictures? We'll wade in with some pictures. That's less painful. So the idea of a random slope is pretty straightforward. I've got 4 combinations of fixed slope versus random slope, existing or not existing, and what the corresponding diagram would look like in each of these cases. So let's say that what we have here are individual slopes for different clusters, and the average slope for my level 1 predictor is given by the heavy black line. So this picture would depict a lack of a fixed slope because on average, the slope is flat. So on average, the level 1 predictor doesn't matter with respect to predicting the outcome. And there is no random slope either, not because the slope is flat, but because the same slope works equally well for each cluster. Each cluster does not need their own slope. They can all share this flat line and it's fine. On the top right here, now we have a positive fixed slope on average, but we don't have a random slope yet because that positive slope works equally well for all the clusters. So in these 2 pictures, these depict what a random intercept model would say the data should look like. The idea that if there's differences between clusters, it's constant no matter where you are on this x-axis. So you only need a random intercept to distinguish cluster mean differences and you're good. Bottom left is when there's not a fixed slope on average, but there is a random slope because each cluster needs their own. So on average, there's no impact of this level 1 predictor, but that's because in some clusters there's a positive slope and in some clusters there's negative, and it's averaging out to be 0. So this fixed slope is misleading in this case, I would say. And now your job got a lot more interesting as the analyst. Why is it that some clusters have a positive slope and some have a negative slope? Well, I don't know. That's now an empirical question. And you can have a mixture of both. So there can be a slope to some extent on average, but the size of that slope differs across clusters. And so yet again, why is it that this slope is stronger in some clusters? Empirical question. All right. To foreshadow the idea of this new random variance, this is going to be a cluster characteristic, just like the intercept is. What kind of predictors do you think I need to predict why some clusters have a stronger slope than others? Level 2 or level 1? 2. Yes, but the way that it works is it does so as part of an interaction term. Cross-level interactions between a level 2 predictor and the level 1 predictor that has the random slope. That's where we're headed. Okay, that's not so bad, right? Just like big picture, different slopes for different folks, or different clusters in this class. It's folks and longitudinal. So in terms of notation, here's a generic example. Then we've got a couple data-related examples. So if I have my within cluster X here, so this is a cluster mean-centered version, where the within cluster X has subtracted the cluster mean off of it, so this has only within level 1 variation. I throw in the cluster mean centered such that 0 means something, pick a constant, doesn't matter which one. So then we have our level 1 within effect and our level 2 between effect. So I've called this between effect of having more of this predictor than other clusters. To be more correct than that even, what should I add to the end of it to distinguish it from a contextual effect? This is more level 1x on average. I would say that is still true, but that would be true of contextual too. What makes this between?
We are not controlling for the original values of the predictor. Of
Yeah,
level one.
not controlling for the original level 1 predictor, because what this is relative information only. All I know in this within cluster X is if it's a positive 1, I'm higher than my cluster. What my cluster is, I don't know. So this is a between effect because we're not controlling for the original predictor. We're only having in the model a predictor that is relative to the cluster mean. That's why this is the between and not contextual. And these two slopes are going to stay the same, more or less, regardless of whether the other is in the model because they are uncorrelated. Now we have our new friend right here, U1. That's my random slope. In the same way that the intercept was how far off your mean you are for that cluster, this is how far off from the average slope your cluster slope is. Same concept. So if y, I need to, that's not a y. Kind of looks like one though. Gamma, thank you. If gamma 1, my within slope is positive, if a positive U1 would mean it's a more positive slope for that cluster, so the relationship is stronger. A negative U1 would mean it is less positive and potentially heading into negative. So the U's are deviations. What they are deviating from is the rest of the stuff that's in the equation for that level 1 slope. Okay, not that yet. How are we doing? So far, so good? One thumb up. Zoomers, doing all right? Zoomers are quiet today. Yeah, doing all right. Okay, cool. Good enough. So why did I do cluster mean centering? The short answer is because you kind of have to. The long answer is much longer. There's a paper that is in press on your reading list that provides the long answer. But otherwise, if I used the original level 1 predictor in here and gave it a random slope, that random slope would be smushed in the same way that the fixed slope would be. Yeah. It's a similar problem with a different consequence, and I'll show you a little bit about that, but that's the short answer. If you want to have a random slope, it needs to apply only to the within part of the variable. Otherwise, there's a different kind of smushing if it applies to the between part and the within part. And here's a picture of random intercepts and slopes that I stole from the internet. It is a well-stolen picture. I've seen this in many, many places, but I actually tracked down the original people who made it. So kudos to them for making a picture that the internet has stolen repeatedly, myself included. So the difference between random intercepts only and random slopes is depicted here. If you have intercepts only, then the slopes are parallel. The differences between clusters stay constant all along this variable, whereas if you have random slopes, that means they're different. So the pink and the green, looks like pink would have a positive U1 because it's more positive than the average. Orange would have a negative U1 because it's less positive than the average. And another implication of this is that if I were to talk about the intercept, I need to be more specific than that because the differences between clusters like on this end of the variable are not the same as the differences on this end. So the intercept is going to become conditional in the same way that the fixed intercept becomes conditional on the 0 values of the predictors with fixed effects. The same thing happens on the random side. And how do I decide if I need this U1? Our friend likelihood ratio test. Same process as testing any kind of random effect. We did variances for the intercept so far. Now we're going to have variances for the slope. And there's one additional piece that shows up when you add a random slope, either by default in some software or you have to add it manually in others. and that is a covariance between U0 and U1. That is not in the equation because covariances don't contribute to predicted values. It does show up in the matrix version of these equations, which will be like 40 slides from now. So when you add a random slope, you are also adding a covariance with the other random effects that are already in the model. So in this case, the degrees of freedom for a likelihood ratio test would be 2, because I'm adding the random slope variance and the covariance with the intercept that's already there. I am not adding any relationship with the e's, though, at level 1. That's separate. Okay, there. Yes,
So-
hit me.
Then this, when you add a random slope, it is not a theoretical question, it is not like a research question decision, it is a strictly likelihood ratio test decision?
Which slopes should be tested for randomness is a theoretical thing, because what you'll find is that they can't all be random at the same time or your model breaks. So which ones to prioritize would be theoretical. Whether your theory is correct and they have differences across clusters boils down to likelihood ratio test, but along with any significance test, though, what do you need to worry about? Yeah, if you're doing a significance test, what do you need to worry about with respect to that test? Like, what if it's non-significant? Does that mean your theory's wrong? Not necessarily, right?
Yeah.
Could be. One of reviewer 2's favorite criticisms? Power. How many clusters do you need to show cluster differences? A lot. So you could end up with a not random slope because you don't have enough power to detect the differences. So there's it's the same interplay as usual. But this is the empirical way to decide. I also have effect sizes that we'll talk about that would supplement this. And you might, bye folks, you might decide to keep it if it's borderline, if it looks like it has a reasonable effect size, or if you need it for further model testing, which not there yet, but yes. So that's the empirical way to decide. All right. Here is the math behind why we need to make sure that we're testing a random slope using the cluster mean centered version. I've written the model out both ways so that you can see the direct correspondence between what it looks like under cluster mean centering right here and constant centering down here. The fixed effects have been made equivalent, so the contextual effect is the same thing as between minus within right here. The within effect is the same either way. And then we get into the random part, and these two are not the same, and they can't be made the same. So what ends up happening if you use cluster mean centering is that the random slope is multiplying only the within part of this variable, only the level 1 part, whereas if you use constant centering, it's multiplying the within part and the between part at the same time. And that is assuming the same kind of heterogeneity of variance across this predictor for both its within part and its between part, which is another kind of smushing that we don't want to do. And here's the paper that is on your reading list that you can get the longer interpretation from. It's fun to read, isn't it, Vlad? Yeah, this is his master's thesis. He's working on this topic, so it's a good time. It's had by all. So the short answer is just don't do this instead. So here's an example. By the way, okay, there. So this started with the workshop that I did for APA in the spring, and I decided to run with this example and build it further. So this is one of the original slides that I had in there. Subsequent slides will have additional models, and the link to that will be down here on each page. So if you want to get the original source materials for these examples and the original data, you can do so. But because I figured at this point we would be like, oh my God, there's too many things on this slide, I took it easy on you and highlighted the things that are new in yellow. So this is an example, just to remind you, where we are predicting language in students nested in schools, and we have 3 level 2 predictors in the model: how much homework the school tends to assign, whether it uses mixed grades, the school's mean for verbal ability of its students, and then a within cluster centered version of verbal ability. So this is cluster mean centered right here. To add a random effect, in SAS it goes on the random line right here, and type equals UN means that the covariance between the random effects gets estimated. In R, it goes inside the parentheses here. So previously we've only had a 1 up to this point for the intercept. Now we have this thing in here for the slope. And R by default estimates correlations among your random effects. You don't have to do anything special with that. In Stata, it goes after the nesting variable in the random part here. And we do have to add covariance UN for unstructured because the default is to not allow covariances among your random effects. And I've also added a line here that allows us to see the correlations themselves. G-core and SAS does the same thing. And last but not least, SPSS, if you're interested in that, you add it to their random line and cove type UN. So as you can see, it's like the same, just with little subtle differences. Is it cove or cove type or covariance? Unstructured, though, for this is the idea of letting all your random effects have whatever variance they want and letting them have whatever correlations they want as well. So here's what the model looks like then, if we have the equation and then the results for this little example. So we have our 3 level 2 predictors predicting beta 0. Then beta 1 is cluster mean centered verbal ability. That beta 1 has a fixed slope here, gamma 1, and to that we've added a random slope. So the fixed effects solution for this model looks similar to what we had in previous examples with these data. The change is in the variance part. So we have a new number as part of our model for the variance, the 0.2239, that's my random slope. That's my random slope variance, I should say. And this is the correlation between the intercept and the slopes. It's negative, so that means that schools that have higher means, when the level 1 predictor is 0, so for like at the average level of the predictor, schools that have higher means have more shallow slopes, which makes sense because if you're already doing well, then there's not much further you can get better in terms of the prediction by verbal ability. And comparing this model against a model without that random slope variance and the covariance with the intercept gives me a significant likelihood ratio test, so yay for me. I would say that it's significant. So this tells me up to this point a binary decision. Yes, there are differences across clusters in the extent to which verbal ability predicts language performance on some test. That's what we know. What's next? Oh, okay. Comparison is next. All right, how are we doing? Yeah, forgive me, I don't have my slide deck memorized because it only existed last week. So I'm going to have to like look ahead periodically. I don't have the version of PowerPoint open where it has the cheaty slide on the side. Yeah, I would not get used to that, by the way, because if you're at a conference, there's no guarantee that whatever computer is going to have the cheaty slide. So wean yourself off of that, would be my recommendation. So what would it look like in terms of the fixed effects if we didn't have a random effect? I just want to make a brief comparison here. So it's this slope that is random or not, the within cluster effect of verbal ability. So the coefficient itself is pretty much the same. For every unit more verbal ability I have than the rest of my school, my language score goes up by 2.44 or 2.42. The reason why these numbers differ is because the ladder here, where we have the random side, actually it's right here, the random side, that one, hang on, yes, that one is just pooling all the data, whereas once you add the random slope, then it's the mean of the slopes. So it's the same issue with the intercept, how it became the mean of the cluster means. This is the mean of the slopes, rather than just one giant slope operating through all the data pooled together. The standard error changes. It gets a little bit bigger because the variance in the slope is adding to it. And that means that the test of that slope is going to change a little bit because the standard error changed a little bit. And note the difference in degrees of freedom. So it looks a lot closer to the level 2 degrees of freedom after the random slope than before. So in terms of like why you should care kind of thing, if you need a random slope, even if you don't care about it, you need it in the model so that the test of the fixed slope is accurate. Question from the Zoomers, could you go over the subscript notation one more time? Sure. So is it the subscripts on the fixed and random effects? Is that the question?
Yeah, well, specifically like the gammas, like having the second zero there. So the first number is the level that you're working with, and then the second number is zero because it's an intercept, technically.
Yeah, so on the subscripts, the first subscript goes with which beta you're predicting at level 1. So all the terms that predict beta 0 for the intercept start with a 0, including the random intercept here. Likewise, all the terms that will predict beta 1, which is the within school verbal slope, are going to start with a 1 for that. And the second subscript keeps track of the order within its level 2 equation, where we start counting at 0. So gamma 0, 0 is the fixed intercept. Gamma 1, 0 is the fixed slope for within cluster verbal. And if we were to add things to this beta 1 equation, it would start 1, 0, and the next one would be 1, 1, because that would be the first predictor of the slope. Can you guess what the next one would be? Kind of a finger question. Yeah, 1, 2, 1, 3, 1, 4. So think of it like a grid, almost. There's like a row column kind of thing happening here. All right, more questions. Can I say again why the standard errors are different? Yes, I can. So on the left-hand side, the standard error is a little bit larger than on the right-hand side because the solution on the left was taken with the random slope and the solution on the right was without the random slope. Yeah, I have boxes here. I'm like, I wrote that down, didn't I? Yes, I did. That was called an animation fail. That's what that was. So with the random slope, there is more uncertainty in estimating the fixed slope because it depends in part on what clusters you have, since the slope varies across clusters. And in addition, the Satterthwaite degrees of freedom change it into something that looks closer to level 2. So the same test will be different after adding a random slope for the fixed effect that it's the slope of. Okay, does that answer those two questions? And there's a third one I'll get to next.
Yeah, I don't know, you can cut me off if this is not related at all, but
Okay, fair.
ordinal, like when we said like ordinal models, and we have the submodels that, you know, for each threshold, it looks very similar to the way that random effects models are set up. And I don't know if I'm trying to make a connection that's not there, but like these are like you have like multiple submodels that define each level like ordinal models would. Is that correct to say?
Yeah, I'll give you that. I mean, they
Okay.
function differently, but the idea that you're breaking up an overall model into pieces, I think is still accurate.
Okay.
This way of specifying it makes it, I think, a little bit clearer what things have main effects and what things have interactions, which is where we're headed. Right now, we don't have any interactions, so that makes it a little bit more straightforward to interpret these things. Next, okay, good with the standard errors. Next one. If you're adding a random slope, the variance would be getting smaller because you're getting more accurate, but it looks like the standard error goes up. Can we explain that? Yes. So, okay. What goes into the standard error for the fixed slope, once it's made random as well, is the random slope variance. And it is pulled out of the residual, but it's not like an even partitioning. What's happening under the hood is that we are introducing heterogeneity of variance. So the total variance is not the same as what it was before. So that additional uncertainty in what the slope should be has to reflect the fact that this is now the average slope across a bunch of slopes. So it's even more uncertain than what it was when there was only one number. Point of the story, what this test shows can change after you add a random slope, but we always keep it. So if the fixed slope becomes non-significant, you keep it anyway. The rationale for that is right here. The fixed slope is what the random slope is varying around, so it doesn't make sense to have a model with just the random part because you're saying that it's varying around exactly 0 rather than whatever this wants to be. Okay, does that help answer the question? Am I heading in the right direction at least? That's my only goal today, the right direction. Sort of. Okay, fair. Question from you?
Yes, I thought that we were estimating the point estimates first, And then the estimator was working with the random part of the model. However, if the fixed part is different, how is Remol estimating those estimates?
So the short answer in terms of estimation is that the likelihood function tries to figure out what model for the variance parameters make the data the tallest. So the random intercept variance, random slope variance, covariance, residual variance in this case. And after it has figured that out, then the fixed effects are computed.
Oh, okay.
And so because you're sort of starting from a different place, these numbers will change a little bit because
makes
they're
sense.
computed
Yeah.
after the fact.
Yeah.
Yeah, and I call that a wiggle because they don't change a lot and they still mean the same thing, but just what they're estimated to be is going to change.
Great, thank you.
Sure. Okay, other questions? All right, so this, go back here, 0.22, is that a lot? Exactly. It's like, well, it's not zero? Is that good? Is that big? I don't know about you, but I have a hard time thinking about variances and explaining them to people as numbers. It gets a little bit easier if you go standard deviation. And so that is the basis of a couple different ways of computing effect size. One is based on our friend random effect confidence interval. So I've got some different numbers in here. Give us another example. So let's say that I have a fixed slope that's 1.72 and a variance around it that's 0.91. So this is from a different problem, but we can use these numbers just the same. So I know that 0.91 is different than 0 because I do a likelihood ratio test to tell me that, but how big is it? So just as we did for the intercept, we can do this for the slopes. We can do this for any effect that has both a fixed part and a random part in these models, which would be level 1 predictors for right now. So fixed effect plus or minus about 2 times the square root of the random variance that goes with it. So that turns it into a standard deviation. So what we're doing here is the fixed slope, which is average, and then like 2 standard deviations around it with respect to the clusters. So if I put in those fake numbers up here into this equation, I get a confidence interval from negative 0.15 to 3.59. So what that tells me is the range that this variance implies around this fixed slope as the middle. The range goes negative, and this can be confusing unless we explain it to our readers carefully. Because when you see a negative value on a confidence interval, what does that normally mean? If the confidence interval overlaps 0, what do we normally conclude?
Not significant.
Yeah, not significant, right? That's not what this means. So I have a separate hypothesis test for whether 1.72 is different than 0. Let's say that it is. And a second one for whether 0.91 is greater than 0. Let's say that it is. So the fact that this interval overlaps 0 doesn't mean that there's some sort of significance issue here. What it means is that some clusters are predicted to have slightly negative slopes. On average, it's 1.7, but the size of the variation around it pushes it into negative territory. So it can go from slightly negative up to really positive. That's what the variance implies. So I think this approach makes it a little bit more intuitive to people, like how different are the slopes? Well, here's the predicted range given the model, assuming that they're symmetric and all that stuff. So explaining this takes a little bit of work, but I think it's worth it in the long run to have a way of expressing this that's a little more intuitive. It's just not the typical confidence interval that's based on the precision of the fixed effect. That's the difference. Okay. Here's another one. You know this one already. How about reliability? This is ICC2. I'm calling it intercept reliability here. And this is very close to the formula for ICC1. The exception is dividing by level 1n. And you might say, why is this times 1? Well, because I'm trying to draw a parallel to what we would do to compute the same thing for the slope. Slope reliability. This is a revised formula that is based on some slope reliability out of the growth modeling literature. There's a classic paper, John Willett from 1989. We took his equation and rearranged it so that it would work for more than just time. So what goes into slope reliability is the size of the slope variance on the numerator plus that the residual variance, the number of people per cluster, level 1n, times the variance of the predictor that it's the slope for. So how big a slope is partially determined by what it is the slope of, right? The change in y for a 1 unit change in x. How many units are there in x? We have to know that for this to make sense. But otherwise, it's still the same idea as traditional reliability. How much of the total variance is due to signal, true variance, versus some kind of noise, where residual variance is being rescaled by sample size and the variable that it's the slope for. So I don't see this reported very much in papers. It's not really a common thing, but you know what I use it for?
Power analysis.
Power analysis, yeah. Because when you do power analyses for these models, the world of like G-power and easy peasy tables and stuff like that is gone. Just say goodbye to it. It was fun while it lasted. Just wave goodbye. Instead, what is much more common and useful, but much harder, is simulation. That's how we do power analyses for multi-level models that have random slopes in particular, simulation. Yeah. What that means is making up a data set that has what you want to happen, replicating that like 1,000 times, and then seeing what proportion of data sets come back as significant with respect to each parameter. That's empirical power. Now the question is, how do you know what to start with if you haven't done a study before, if you don't have answers, right? Like you can't just pull something out of the air. Well, you can reverse this formula to start from somewhere. So if you say, I want to have a slope reliability that's 0.8, and I know what the variance of the variable is that I'm estimating the slope for, work backwards, and you can solve to figure out what the variance must be. That would generate a reliability of 0.8. Then you're in business. This is one of the units that we may not have time for, but I have some stuff. I have some spreadsheets and some code and stuff that I can share with you where I've done this sort of thing a lot for grant analyses and kinds of things. Looking unhappy about that.
So, how do we create the data set? So we have something we want to happen.
Mm-hmm.
And that equation is how we create the data set for it?
That is how we make a reasonable guess as to what the slope variance could be.
Okay.
It's complex, I'll tell you that. But this is what I use this for in practice. You can get pretty far with made-up numbers, but you can't get random slopes very easily that way. Mm. So like, let's just make up a number, right? Okay, my outcome is going to have a total variance of 1. Okay, I can make a reasonable guess as to what the interclass correlation is based on whatever context I'm working in. Let's say it's 50-50. So then I can figure out, well, if my total outcome variance is 1, then that's 0.5 for the intercept and 0.5 for residual. And then if I want a slope reliability of, let's say, 0.8, I know how many people I'm going to have per cluster. Let's say that x is another variable with a slope variance of 1. I can use those numbers to work backwards and come up with the slope variance. Otherwise, it's much trickier to try and figure out what that should be. So that's what I use this for. And also meta-analysis. Yes, you can, if you wanted to somehow combine estimates of slope variances from different things, I guess you could do that by converting it to reliability. I haven't seen that before, but it seems like a thing that one could do. All right, intermediate summary. See, look, we've already gotten to the point where we get to summarize. Doesn't that feel nice? No? Yes? Yeah, I think so. So in terms of what we have to worry about of fixed versus random, level 1 only. So level 2 predictors are cluster things, right? They're going to explain why some clusters have higher means than others. They can have fixed slopes only. Technically speaking, there is a random slope, but it's not really a slope, and I don't want to get into it. It's too ugly and uncertain. But as an example, if I had school achievement, I might ask if it varies across type of school, such as rural versus urban. Level 1 predictors are people things. So they can have fixed slopes and they can have random slopes. And the two work together. So as a classic textbook example, if I'm looking at student achievement and I have student socioeconomic status, otherwise abbreviated as money, as you gave me permission last week. Do I still get that permission? Okay. So student money relates to student achievement. The fixed slope is there a relationship on average? Do students with more money have better achievement? Or the way that it's usually phrased is, do students with less money have lower achievement? Like a gap of performance, some kind, or a disadvantage. So if there is a disadvantage related to money, on average, that's your fixed effect. Does the extent of that disadvantage depend on what school you go to? If so, that's a random effect. The idea is that the gap varies across clusters. The way of operationalizing that idea of a money-related gap is a random slope. So the fixed slope applies to the level 1 predictor. The random slope applies across clusters. So it's a level 2 random slope variance of a level 1 predictor.
Can I ask a silly question?
I love silly questions.
So, the contextual effect, what we previously talked about,
Mhm.
you described as what happens if you move schools to a different school. So is this, I know they're different, but like if you were to write it,
Mm-hmm.
I guess how would you talk about both contextual and random? And if we get to
Yes.
this later, that I'm just.
No, I want to answer it now. It's a good question because trying to make these things concrete. Can we stick with money as an example? Okay. So the less money you have, the worse you do in school. We'll say that that's your level 1 effect. Now, after controlling for how much money you have, does how much money everyone around you has, yeah, I think that's grammatically correct, does that predict achievement? So the latter is the context effect. Like if I took myself and my money and I moved to a new school, how much does that new context additionally predict the school's achievement? Because context is a school level thing. If I don't control for my own money, then it's a between effect instead. So within plus contextual equals between. Okay, so that is talking about a main effect of level 1 money. So the less money I have, the worse I do. Then there's a level 2 main effect of school mean money, which is above and beyond my money, because that's the way I'm setting it up here in the story. So that is just describing differences between schools related to money, on average differences, so just intercept differences, and average differences between kids, the haves and the have-nots. Now where we're at it here is, let's say that in one school, if you get, let's say free lunch, right? That's the marker that people use for money. That's what example 4 has. Let's say that if you get free lunch, that your slope indicates you do 10 points worse on this achievement outcome. And in another school, kids who get free lunch only do 8 points worse. In another school, kids who get free lunch do 12 points worse. So that idea that the relationship between level 1 money and level 1 outcome varies by school, that's a random slope. So that's a separate thing. So that's a separate thing, but we're going to end up at the same place, potentially, where the extent to which some schools have a steeper penalty for being poor is going to be predicted by level 2 school characteristics. Why is it that some schools are more egalitarian and some schools are less so? That's a new question we get to ask. So random slopes represent another way that clusters differ meaningfully from each other, not just in intercept, but also in their SES gaps in this example, but the effects of level 1 predictors more generally. Good, thank you for asking. Other questions or other examples?
Lisa, would it be correct to say, like using the SES and achievement, the fixed effect at level 1, so the intercept, is the average after controlling for variation between clusters.
I wouldn't say it's controlling for, but it is it's the mean of the cluster slopes, is the way I would say it. It's the average slope.
Okay. Would it like above and beyond variation in the clusters, or is that also not right to say?
I wouldn't say it that way because what we're talking about is a specific kind of variation.
Okay.
Can I skip ahead like 60 slides and get to a picture that I think might help?
Yeah, sure, as long as we go back.
As long as we go back. Yeah, said no one ever. Like, no, you can skip 60 slides, that's fine. Like, no, we're not skipping these slides because these slides have my blood, sweat, and tears in them. So, if for no other reason than that, but this is the one I wanted. Isn't this pretty? Okay, let's see if I have an animation fail. No. Okay, so this may help. So once upon a time, we had an outcome. And it had all of its variance in one pile. And the first thing we did was split it up. So we're saying, okay, now I have my empty means, random intercept, two-level model. Some of my outcome variance is due to between cluster differences, mean differences, and some of it is because people from the same cluster are different from each other. Okay, so then we added some predictors, such as within cluster money and between cluster money. Or we could have the non-cluster mean-centered version, and this would be the context effect. So either way, this would be a within-school effect. Why is it that some kids have higher outcomes than others? Well, maybe it's because of this kid characteristic. Why is it that some clusters have higher outcomes than others? Maybe it's because of this cluster characteristic. Cool. So we reduce some of the variance, we reduce some of the variance. Now, what if I want to know if the effect of my kid predictor varies over clusters? Where's that going to come out of? And let the colors help you answer that question. If I want to add a random slope, the extent to which having more money than other people affects your outcome varies by cluster. Where is that going to come out of?
From the residual variance.
It's coming out of here. That's what happens. So part of the reason why it looked like people were differing from their cluster means may be because that mean was being created by one slope, whereas each cluster needs their own slope. So part of what we were calling error and within school differences is actually between school differences. So then the intercept stays the same, although it becomes conditional, and we're left with just these three piles of variance. So I'm putting a box around them to show that this is where we end up. The green circles have a covariance. Your intercept for your cluster gets to be related to your slope for your cluster. And I have the level 1 residual is mostly purple, but there's just a little hint of green in it. What if I have another very theoretically important level 1 predictor? Can I give it a random slope?
Yeah.
I can try, right? Where's that one going to come out of?
Residual variance.
This one still. So the objective of the game, more or less, is to keep pulling things out of that residual until what's left is truly just within and people are conditionally independent. We don't ever know if we get there, but that's the objective. And then the question is, what kind of predictors would account for each of these sources of variance? You know this one. How do I reduce my level 1 residual variance? What kind of predictors?
Level 1.
Level 1, otherwise known as people things. Why are some people still higher than others? I don't know, people characteristics. How about intercept variance at the bottom here? Why are some clusters higher on average than other clusters? What predicts that? Why are some clusters higher than other clusters? What kind of predictor would we need for that? Not people things. What's the other choice? Cluster things, yeah. Now this guy, right here, the slope, this is the tricky one. This is between cluster variance in a within cluster slope. It's kind of both at the same time. Between cluster variance at level 2 in the within cluster slope of a level 1 predictor. So if it's kind of both at the same time, what kind of predictors would capture it? Kind of both is the answer. This is cross-level interactions, such as whatever this cluster characteristic is. So the level 2 predictor interacting with the level 1 predictor, the random slope is 4. That's what we need to be able to predict slope variance. Yes.
Is that in the case that we will have intercept heteroscedasticity or heterogeneity in our random slope, that would be another color?
It would, but that's not part of my story.
Great.
I am not going there. This is hard enough.
That would be interesting.
Yeah.
Yeah.
So then putting your question onto the picture, okay, here's my within effect. This is either contextual or between, based on what version of the variable it is. So those are separate from this effect getting its own variance across clusters. That is explained by a cluster characteristic interacting with the level 1 predictor that this is the variance for. So if this were let's stick with money. If this is like within school money and between school money, why is it that the effect of being poor varies across clusters? Well, maybe it depends on how poor your school is. If everybody's poor, then it's not as much of a big deal, maybe. So then that would be a cross-level interaction between the two halves of the same variable. Does the context that you're in with respect to money capture why it is that the disadvantage at the student level varies across clusters? See, and you thought this was a math class, right? It's all about English. All these words to go with this. It's crazy. But the good news is this is kind of the end of new concepts. Like once we get this, we're kind of home free. Just little tweaks on things you already know. And this is only 42 slides in. It wasn't 60. We only skipped about 25 or so, give or take. Okay, does that help at all? Maybe? Yeah. We're getting there. We're getting there. It's hard. It is tricky stuff. I'm not going to lie to you. Okay. Not that far. Not that far. Here we go. Okay, so there's the recap. If we're doing significance tests, we want to keep the fixed effects the same so we can stay in REML. Then we can ask whether the random slope variance helped the model made the data taller, including its covariance as well. Okay. So the idea then, big picture, random slopes are another type of way that clusters differ from each other. That's what I want you to hang on to. What's happening under the hood, though, and I will show you the math as to why it is this way, this is the end result, is that we are introducing heterogeneity of variance in our outcome. Random slopes create different variances depending on what your standing is on the level 1 predictor that has the random slope. And the pattern of heterogeneity is quite specific. It's actually quadratic. This is the model implied variance function for a within cluster X slope being random. The 2 there means that it's creating a quadratic function like a U, like this. Yep, exactly. Like a happy face. Like all of you will get on your faces in about 15 minutes, or no, 10 minutes when it's time to leave. That kind of happy face. What that means is there's some point where the variance across clusters is minimized, but as you move away from that point, it grows. So it's a particular kind of heterogeneity of variance in this quadratic fashion. So the idea then is that random slopes themselves don't explain anything. They are creating a new pile of variance. And yes, I will die on this hill. They are another kind of variability across clusters that we don't know why it is. We know that there's a difference in the effect of money across schools, but we don't know why it is that way. So it's another source of random cluster differences that we have to predict. So not just main effects, which are in charge of mean differences, but now potentially slope differences between clusters as well. Two different things. And what accounts for slope differences are our friends' cross-level interaction, another new concept. It's like this. So now we're adding to the beta 1 row here. And I'm using the same variable that is used in the beta 0 row. Doesn't have to be, but it should be in most cases. This is in particular an intravariable interaction because it's between the two parts. Now, it's not obvious that this is an interaction when you look at it, but if you, in your mind, like scoop all this stuff that's inside beta 1 and bring it back up here, when you multiply it out, it creates gamma 1, 1 is the interaction of cluster mean for the variable and the within cluster version of the same variable between the pieces. You're laughing at me. Go ahead.
I've taken, this is technically like the fourth flavor of this class I've taken. Cross-level interactions always mess me up. This is the first time I've gotten it.
Okay, so that's why you're laughing.
Yes.
Okay, so everyone who's listening, 4 classes is what it takes for this to sink in.
Oh,
Yeah,
so that means in 8 more years.
in 8 years.
So,
Yep, and it was approximately 2002 when I started trying to teach myself this shit. And I feel like I'm close to getting it. Close, but not quite there yet. So yeah, that's completely accurate. Yep.
Wait.
Mm-hmm.
I mean, I trusted it was cross-level because it's on the slide that it says it's cross-level, and the connection of like, that is why it's cross-level, like, that is what just sunk in for me.
Oh, okay, that works. We take our victories where we can. All right. Okay, so cross-level, because it's multiplying a level 1 variable times a level 2 variable. That's where the term comes from. In this case, it's another label of intravariable. I think I made that up. I probably didn't, but that's a term that I use. I know that. Because these are the two halves of the same thing. So the two parts of the same variable are interacting with each other. Does the effect of having more than other people depend on how much other people have? That's the idea. More than your cluster does depend on how much your cluster has as an overall. I'm mixing my longitudinal now into this. Damn it. I've done all so well this semester without saying it, and I'm starting to screw it up again. Okay, I'll say that again correctly. Intravariable, because the effect of having more than the rest of your clusters is moderated by how much your cluster has on average. There we go. The effect of having more than your cluster is moderated by how much your cluster has on average. That's what this model is saying. Yeah, and I've all written down. Okay, there we go. Then we get into simple effects. So this new cross-level interaction here, which kind of variance is it going to account for?
Level 2
Level 2,
should be.
it is, but more specific. How many kinds of level 2 variance do I have in the model at this point?
2.
2 kinds. I got a U0 thing and a U1 thing. Those are 2 different ways that clusters differ from each other. Those are 2 different variances that are up for grabs. My cross-level interaction here in yellow, which one is it going to take?
Random slope.
Yeah, the one in its equation is always the answer. So U1 is how far off my cluster's slope is from the average slope for this level 1 x variable. Part of the reason why my cluster might be higher than other clusters in terms of our slope is because of this characteristic. If so, then this variance should be reduced. So that means how many pseudo R squares are we talking about at this point?
3.
3.
Oh boy,
Uh-huh.
I can just foresee what's going to happen in the homework, and I'm a little nervous. In true transparency.
Well, this homework has not been created yet. And I can tell you that it will not be due when the original syllabus said, because we're a full week behind. So I got to figure out what I want to do for it and how crazy I want to make it. I'm leaning towards not crazy, though, in the interest of full transparency.
Hey, I'm here for it.
But yes, this gets complicated. So now I've got 3 different kinds of variance to keep track of in this model. Why are some clusters higher on average? That's U0. Why are some clusters, do they have a stronger slope of this person predictor than other clusters? That's U1. And then even after I take into account all that stuff, why are some people higher than other people even though they go to the same cluster? That's E. Should I say that again?
So if you could repeat the U1C again.
U1C, that's my random slope.
Yep.
That's how far off my cluster slope is from the mean slope of this level 1 person predictor effect.
Level 1 person. Thank you.
So, kinds of variance, each one means something different. Why are some clusters higher than others on their outcome on average? That's U0. Why do some clusters have stronger effects of my person predictor? That's U1. After controlling for all that stuff, why are some people higher than others even though they belong to the same cluster? That's E. And in an ideal world, each term that you add to your model would target only one of these things. But there's a reason why they're called pseudo R-square. They wiggle. And you'll see that in the examples. It's true, it always happens. It never works as cleanly as it does in the textbook examples. Unless you have like an R-square of 0.8 or something, then it's pretty well like fake, but you know. All right, so this is an interaction. Let's end with that. What are the rules for interactions? What happens to their main effects?
Can be more or less positive or negative.
There's only 4 kinds. More positive, less positive, more negative, less negative. But the main effects, you can't just say this is the effect of X, right? This is the effect of X specifically when its interacting predictor is 0. So in this case, it looks a little crazy, but gamma 1O, that's the main effect of my person predictor at level 1. That is now specifically when CMX as the interacting variable is 0. So conditional, simple effect is the term for it, even though it's complicated. Likewise, gamma O1 is the main effect of my level 2 predictor, which is my cluster mean, specifically when its interacting variable is 0, which is the other one. So this is the between effect, specifically when people are at their cluster mean, because that's when with this within cluster X is 0. The cross-level interaction, so named because it is interacting a level 2 predictor with a level 1 predictor. You can talk about either way. It is how the within effect gets stronger by the cluster mean, or less strong, weaker, or it's how the cluster mean effect gets weaker or stronger as a function of the within. It's usually the first one is easier, so I did it that way. So this is the idea of the person slope, person predictor having a slope predicting people outcomes. The interaction term is going to make that more positive, less positive, more negative, or less negative. And in particular, the coefficient is how that slope changes per unit of the cluster variable. Ta-da! That's the only other new concept. The rest of it is a lot of elaboration. Okay. How we doing? This hurts, right? It does.
I think these models are reliability is so complex.
The models are complex?
Yes.
Yes.
And reliability is so complex. Like results is confusing.
The results can be confusing, yes. And this is part of the reason why I'm making a big point about putting words on ideas, because that's how you keep people with you to understand this. It's not just, oh, this variance and that variance. It's like, no, we got to keep in mind, what is this the variance of? What does it mean? Then we can help to pull apart the story. But it is complicated. Yeah. Maybe in another 20 years it'll be easier for me, but I'm not there yet, so. I don't want to make it a self-fulfilling prophecy, like, this shit is hard, but I also don't want you to feel bad if you think this shit is hard, because it is. It is. It is what it is, so. All right, on that happy note, any other questions or things you want me to say again before we call it a day? A Tuesday, happy garbage day.
Yeah, I have one last question. So this is based on the Lois paper and the problem with conflated interaction effects.
Yes.
So if we have two level 1 effects within cluster effects at level 1, and we want to see if an interaction between those two terms is helpful or not, why conflated interaction effects is a thing there if we know that the within part is orthogonal with respect to the between part?
Because when you multiply two cluster mean centered variables together to create the interaction term at level 1, they will have level 2 variance in them.
Anyway,
Yeah,
wow.
a little bit, not a lot, but a tiny bit.
Okay,
So there's
yeah.
an order of operations issue if if you center then multiply or multiply then center.
Exactly, yes.
And the latter removes it, but it makes it weird. So we're not
Okay.
doing that as an example.
Great.
I'm not going down that road either. So, but I could make it worse. That's your take-home message. It could be worse, but not today.
Yeah, it seems weird.
Yeah. All
Thank
right. 1:45. Time to shut up. Thanks for being here. We'll keep struggling with it. We're gonna keep pushing through. See ya on Thursday, folks.
Just have to remember